In this video, we are going to process this dataset of Burushaski in English, or the Roman Burushaski dataset. As we saw in the earlier video, it has a total of 414 sentences, each sentence as a separate document, and this is what we have as the dataset. So now we are going to get to the code part, read this dataset and perform some basic analytics on it. So this is the code that we have already written. So we are just going to walk through this code and see how we can process this dataset. So first, we have read this dataset into a local variable data.txt. So we are going to open the document and read everything from it into the variable raw data. So we would run this command and we have everything in this variable raw data. So if you run this command, we have read everything in the dataset in this variable. If you walk through this, so we can see that there are some numbers. We can see those numbers over here also. They do not mean anything, and we would want to get rid of these numbers because we want to perform analytics on the words of the actual sentence, and these numbers are not going to make much sense over there. Secondly, it's a very small data set with very few punctuations, but still we would want to get rid of these punctuations that we can find here and there, just because we want to perform analytics on the actual words, and we are not doing something complex for which we would need punctuations, so we would want to get rid of them as well. You can see these new line characters, they basically represent the next line. So over here we have each sentence on a separate line, which is represented by this new line character over here. So we would also want to split it into a list of all these sentences. At present we have everything as one string in this variable. So we would just comment this out. And now before proceeding, we would clean the dataset by removing all the punctuations that we talked about. There is a list of punctuations available in the string library. So we are importing string, and from string.punctuation, we are getting the list of all punctuations and we are storing it in this variable punc. So if you want to see what we have in punc, so these are all the possible punctuations that we could have in the dataset. So we would parse this dataset in comparison to these characters, and if there is a match, we would want to get rid of all those characters because at present we are not interested in keeping punctuations. The same way, we are also not interested in digits. So we have this little piece of code over here that is going to do this job for us. So we have defined this variable data and have initialized it to null value. We are iterating through the raw data, which has all the dataset character by character. And if that character is not in this punc string, which means it's not a punctuation, and the function ch is digit also returns false, which means it's not a digit. So we are adding that character to this data variable. So we are parsing each character of the raw data. If it is not a punctuation, not a digit, we are adding it to this data. So basically data is the cleaned form of raw data that has no digits and no punctuations. After this loop completes, we are splitting this data variable, which was originally a string, on new line, which converts it into a list of strings. So in case we want to see what we have in data, so now we have exactly the same structure as we had in the actual data set. We have a list of strings, and each string is having that one sentence or document that we had in the original data set. In case you want to see the total number of documents that we have, it's 415. So in the original data set, we have 414 documents. So there is a mismatch over here. We would want to see what is the first document that we have in this data set. So it's the first document that we have in the actual data set. So the start of the data set is being read correctly. In case we want to see what is the last document of this list, so the last document is a null string. So this is an issue that may give us some runtime errors because we would be performing some analytics. We might be splitting this sentence on words, and it's going to give us an error because it won't have any words. So it's better to get rid of this and get in order to avoid any errors in the future. So for that, we are going to call the function data.remove, and we are going to pass this last item to it, and that is going to Oh, we have missed a bracket. So that is going to get rid of this last item of the list, which was a null string. Again, we would want to see the last item of the string. So it's a meaningful sentence now, which I would expect would be the last sentence of this data set. So we have got a match with this. And if you want to see what are the total number of documents that we have, it's 414, which exactly match what we have in the dataset. So from here, we have ensured that we have read all the dataset correctly, and we have also cleaned the dataset by removing punctuations and digits. Next, we are just to be on the safe side, we are also stripping off all the white spaces from the dataset or the sentences that we have on each side. They are meaningful when we have these white spaces between words, but otherwise if we have multiple white spaces before or after the start or end of the sentence, we do not want those white spaces. So this function strip is going to get rid of all the unnecessary white spaces. We could have any other characters at the start or end of the sentence, and we can simply get rid of it using the same function by passing that character to it over here. So this is going to get rid of all the dots that are at the start or end of the sentence. So any delimiter that is coming from the format of the source from where you are reading the data could be removed using this process. So the first thing that we are printing is the total number of documents that we have. So that is the first analytics that we have performed. So the first thing that we are printing is the total number of documents, which is 414. Next, we want to see what are the total number of words in this data set. So data, as you remember, had a listing of all the sentences. So we are combining all the sentences on space. So now we have just this one big sentence that has the words of all the data set, and we are splitting it again on space. So basically, all words is going to have a list of all the words and not just the words of a single sentence. And when we call the function length on it, it's going to give us the frequency of all the words in the dataset, which is 1992. So this is the total number of words that we have in the dataset, or you can say the size of the dataset. Next, we want to find out what is the longest and the shortest sentence in the dataset by the number of characters and number of words. So we have defined this max length w character and max length variable and max length c variable. Both are initialized to 0. So we are iterating through each sentence. Then we are finding the number of characters in that sentence. If it is greater than max length c, which is initialized by 0, so the number of characters of the first length would be assigned to it. And then each time we have a sentence bigger than that in terms of number of characters, it's going to replace the value in this variable. In the next part, we are splitting the sentence, that is the item in the data, on space. So it's going to give us the listing of all words, and then we are applying the length function on it. So the length function over here is giving us the total number of characters because we have a complete string of or a sentence passing on to it, and over here we have separated it into words. So it's going to give us the number of words, and we are doing exactly the same thing, that if the value is bigger than the max length w, so replace the value. After running this code, we have the longest sentence that has a total of 144 characters, and the longest sentence by words has a total of 24 words. We are going to find out the shortest sentence by characters and words, and for this we just need to initialize these new variables by some big value and reverse the operational characters, and the rest is going to be the same, and that is going to give us the shortest sentence by characters, which is 8, and the shortest sentence by words is 2 words. This could have been the same sentence, however, we haven't preserved the actual sentence, so we cannot say for sure. If we would have a variable that would keep on preserving or updating the sentence each time we update the value of this variable, so we would know what sentence these are. Next, we would want to find out the unique vocabulary in the dataset or the complete list of words. So for that purpose, we are using this dictionary wordfrac, and we are iterating through the all words, that is having all the words of the dataset. This variable is what we used earlier, so we are iterating through each word of the dataset, and if that word is not in this, and if that word happens to be in the keys of this dictionary, so we are basically increasing its frequency as value by 1. If the word does not exist, so we are adding it to the dictionary and its frequency or value is initialized with 1. So this is going to give us so this dictionary is basically having all its keys as the unique words and its values as their frequencies. If we would just apply the length function on it, it's going to give us the listing of all the unique words, which in this case is 702. So as you saw earlier, the total number of words in the dataset are 1992 and unique words are 702. In this part, we are going to again parse through all the words that we have, but this time we are interested in the most frequent words. So if we could just have reverse ordered this dictionary, that is going to do the job for us. However, we are just again repeating the process, so we could have avoided it by using this same list dictionary that we have already generated. An important thing over here is that we are using the default dictionary instead of the basic dictionary as we have used over here, and the difference is that if you are looking for a value in a dictionary and the value does not exist in that dictionary, this dictionary is going to give you an error, while the default dictionary is going to give you a value of 0 because that key does not exist in the dictionary. So this is the difference. Just to avoid the error message, if you use the default dictionary, it's going to give you 0 frequency or value for all the keys that do not exist in the dictionary. So we are basically sorting the dictionary that has the words as its keys and their frequencies as values. We are using the reverse sorting as true because we want it to be in descending order, and we are interested in keeping the top 5 words. So if you run this code, it's going to give us the 5 most frequent words in the dataset. These are the words and these are their frequencies. In order to get the most infrequent words, we would just make the reverse ordering false, which would keep it in the ascending order. And again, we are interested in only the top 5 words. So these are the most infrequent words and they are all having frequency of 1. Next, we want to see the longest and the shortest words. So we have defined these variables and have initialized max WL and main WL and have initialized them with very small and very large value respectively, and we have initialized their string parts with null strings. So we are iterating through all the words that we have in this all word list. On this all words list, we could have used the unique set of words, which would have made this code a lot efficient. However, this would still do the job. If the word is having a length of greater than max length, so we are updating the value of max WL by the length of that word in terms of number of characters, and we are keeping that word over here. Each time there is a word that has length bigger than this value, the word and its length are going to get updated. The problem is this has words repeated more often, so that isn't going to help us and would just cost extra computation. So the unique set of words would have saved those computations for us. The same way, using the same loop, we are also looking if the word has its length less than this value. So in that case, we are updating the value of this variable that is keeping the number of characters of those words, and we are keeping the word over here as well. We have a condition over here that the word length must be greater than 0 just in case we have by mistake a null string. So if you run this code, and the longest word that we have is this one that has character length of 14, and the shortest sentence is E that is having 1 character. In case we want to see the total the average words per sentence, so we would run this code. Over here we have all the words, over here we have all the sentences when we call the for length function on it. So the length or the size of all the words, that was I think 1992, and the length of all the documents, that was 414. So that is going to give us the average value, which is 400, which is 4.8. So this is the average size of a sentence, or the average number of words that we have per sentence. The same way, this is having all the characters of the dataset, and this is having all the words of the dataset. So if we call the length function on it, that is going to give us that size of words. So if we divide it with this, it's going to give us 5.04, which is basically the average length of a word in terms of the number of characters. So that was some basic analytics that we used on the dataset. Next, we would want to see something more interesting. So for that, we would need these additional libraries. We would need the wordcloud and the matplotlib libraries. So I have already installed them. So therefore, I have commented them out. So in case you haven't, so you would have to run these codes to run these two commands in order to install those libraries first. So we have imported them over here, and we have created an object of wordcloud, and we have passed some parameters to it. What would be its size, the random initial state, the background color is set to silver, and we have called the function generate on it. And to this we have passed the raw data. We should have passed the data variable, which was the clean data, but this would also do the job for us. So we are then using the matplotlib library that we have named, for which we have used the alias as plt. So we are calling the function figure that is going to give us the size figure, and we have set the figure size to 40 cross 30. We want to present this wordcloud in this figure, and we do not want to show the x's. And then finally running plt.show would present the figure to us. It's going to take a while, and it's ready. So this is the word cloud that we have based on the parameter settings that we provided. As you would remember, this was the most frequent word in the dataset, so it has identified the prominent words and have sized them based on their frequencies and have presented them with different colors to have the most important or significant vocabulary of the dataset in this one picture. Next, we are going to perform some topic modeling on this dataset, and there are different ways of doing it. We would want to have some visualization of it as well, and we would also want to have the listing of words. So we are using this PyLDAWIS library for this. Again, it's just used for visualization. If you're not interested in visualizations, we can just skip this part, otherwise you can install it. So over here, topic modeling or LDA can only be applied to numeric form of the data. We cannot run it on raw text. So therefore, the first thing that we need to do is to vectorize the data, and for that we are using these classes count vectorizer or TF-IDF vectorizer. For the sake of this example, we are using the count vectorizer, and we have commented out the TF-IDF vectorizer, so it's up to you whichever you use. Count vectorizer would represent the words in the documents by their count frequencies, while TF-IDF would replace them with their real TF-IDF values. So that is going to represent the whole dataset in numeric form, that is in the form of a matrix where the number of columns would be equal to the number of features or the unique set of words that we have in the dataset, and the number of rows would be equal to the number of documents that we have in the dataset. This is how, so over here we have created an object of count vectorizer, and we have applied some settings on it. We want the stop words of English to be removed. So basically it's not going to make much sense because English stop words won't apply, so we can get rid of this. We want everything to be in lowercase. Again, that would make a lot of difference, because if a word happens to be the first word of a sentence, and if the first character is capital, so it's going to consider them as two different words. To get rid of this problem, we are converting everything into the lowercase. Then we have this regular expression as a condition on the type of word that we were interested in keeping. So this R and quotes basically stands for regular expressions. \B stands for break. So basically this rule is going to be applied on individual words, and it's not going to be applied as characters that could be the middle characters of a word. So that's why we have these \B on each side of this pattern. And in between we have A to Z small and capital. So basically we want words that have only letters, not punctuations, digits, or any other characters, and the size must be 3 or greater than 3. So this is the restriction on the dataset that we have, that we are only interested in words that does not have any other type of characters, and its size must be 3 or greater than 3. Then we have applied another condition over here where the maximum document frequency is set to 0.5 probability, which means that all the words that happen to be in more than half of the documents, those are more often stop words. Get rid of those words. The minimum document frequency is set to 2. So a word that is in less than 2 documents or 2 documents, that word is also a noise word, and we would also not want to have that word. So using these parameters, we have created this object TF vectorizer, and to this we have passed our data. So this would basically give us the structured data. In case we want to have a look at it, we would just skip this part for now, the visualization part, because we haven't walked through that code. I would just want to show you this TF data values. So this is what we have in TF data. We have a matrix of 414 cross 242. So this 414 is the number of rows of the matrix, and 242 is the number of words. If you remember, the unique words were more than 700. However, after applying all these conditions that we just set in the parameters, the words that we presently have are 242 to represent this data set. In case we want to see the actual dataset values, so it's a compressed dataset, and that is having lots of zeros. We have these dots in between because it cannot just show us the rows with 242 values. So this is the whole dataset. This is the whole dataset vectorized into rows and columns and represented as numeric values. It's going to have lots of zeros because it's a sparse matrix, and if we have 242 columns or unique words, one sentence is going to have 3 or 4 words, and the rest of the values are going to be 0. In case we want to pick a specific, let's say the first sentence, and see how it's vectorized. So this is the vectorized form of the first sentence. We have a total of 242 values, where you would see few ones, and then the rest is all zeros. So basically this is the complete set of values, or the vector that is representing the first document in the dataset. Get feature names out is going to give us the listing of all these words, so that would associate some meaning to these values that we have. So in case we want to print what we have in features, it's features. So these are all the unique words that we are having to represent this data set. So the first word is this one. So this first 0 represents that this word is missing in the first document or sentence. The second word in the sequence is this one, which would be represented by this 0 in the first document. So again, there will be some ones for it down the line in other documents, but this is the exact ordering and the complete list of all the words that we are using as features in this case, that is after applying all these conditions. So then we have created an object of the latent Dirichlet allocation, and n underscore components is set to 5, which means that we are applying topic modeling and the number of topics are set to 5, or in other words, we want all these 242 words to be separated into 5 different groups. So we have trained the model on this data set, and then using this library that we just imported, we are basically trying to associate some visualization to this topic modeling. So this is what we have. These are the 5 topics that we have. So topic 1 is over here, then we have topic 2 over here, 3, 4 and 5. So 1 and 4 are very much alike, and then 5, 2 and 3 are different among themselves and from 1 and 4. So these are the 5 topics, and these are the prominent words in the data set that we have, represented by their frequencies. In order to dig deep into these topics, we would just use we already have a trained model, but we would just want to represent them differently. So we are iterating through the 5 topics that we had in this trained variable, and we would want to see what are these topics and what are the top words of these topics. So basically we are iterating through these 5 topics. We are printing the topic ID, we are printing the IDs of the words that we have in their topic, again in reverse order, because we want the words with higher probabilities to be printed first because they have highest relevance with the topics. Then we are printing the probabilities of those words again in decreasing order, because the higher probability, the most relevance that word have with their topic. And another thing to note over here is that these are raw probabilities, so the values are going to be above 1. We could have normalized it to bring all those values to the range of 0 and 1, but that would just cost extra computation and it's not going to affect the ordering of words. So since we are just interested in the ordering, so we are going to use raw probabilities instead of the actual probabilities. And then the actual word, this is the most important part that we are interested in. What are the words that we have in those topics? So if we run this is what we have. We would just apply a restriction on it, because generally when we are looking into the words of a topic, we are not interested in all the words. We are just interested in the top few words. So let's say we are representing these topics by their top 10 words. So we would do the same for all the 3 sets because they run concurrently with one another. So these are the top, this is topic 0, and these are the top words having their word IDs. These are the probabilities or the raw probabilities of the top 10 words. So as you can see, the first word has raw probability of 16.14, then 13.48. So these are all the words having raw probabilities. So basically this shows their relevance with the topic. So this is the first word on the list which has this raw probability and this ID. So it has the highest relevance with topic 0, and then followed by this word and then this word. So we are just representing the top 10 words which are the most relevant words for topic 0. Then we have the topic ID for topic 1, and followed by its words, the IDs of the words that are more associated with it, their raw frequencies, and then followed by the actual words that we have in this topic, and the same way we have for all the other 3 topics. So basically the purpose of showing this was just to give you an idea that what are the words that we're dealing with. We are generally not interested in the word IDs and their raw probabilities, so we are just interested in the topics and the words that we have in those topics, and the list would go on, and the probabilities would just get smaller and smaller. But we are not interested in long list of very small probabilities. We just want the top few words with good probabilities to represent a topic. So that was some basic analytics on this dataset, and see you next time. Thank you.